Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In the earlier sessions, we have dealt with random variables, discrete and continuous. Associated with the random variables, we have also called, we have one more thing called a sequence of random variables. For this sequence of random variables satisfies 2 laws of large numbers. One is called a weak law of large numbers, another one is called strong law of large numbers. In the earlier sessions, we have dealt with the sequence of random variables satisfying one inequality called Chebyshev inequality. Now, in this session, we are going to deal with the statement and proof of weak law of large numbers and also the statement and proof of strong law of large numbers. Some exercises also will be worked out in weak law of large numbers for IID random variables, which is called identically and independently distributed random variables. So, the first one, weak law of large numbers statement goes like that. Let x1, x2, etc. up to xn be a sequence of random variables and mu1, mu2, etc. up to mun be the respective means, and let bn is equal to variance of x1 plus x2 plus x3 plus etc. plus xn. If it converges, then a probability of modulus of x1 plus x2 plus etc. plus xn by n minus mu1 plus mu2 plus etc. mu n by n is less than or equal to epsilon is greater than or equal to 1 minus eta. For all n, this particular n is greater than n naught. N naught is a fixed number which is depending on this epsilon and eta, where epsilon and eta are arbitrary small numbers, positive numbers, provided limit n tends to infinity, bn by n square should tend to 0. If we want to test whether a sequence of random variables is obeying WLLN, that is weak law of large numbers, we have to verify this particular condition, that is as n tends to infinity, bn by n square should tend to 0. This particular statement is given in the previous session. In this session, we are going to deal with the proof. How the proof goes? For the proof, we need the Chebyshev inequality. That is, Chebyshev inequality has to be applied for x1 plus x2 plus etc. plus xn divided by n. What does the Chebyshev inequality says? This Chebyshev inequality already dealt in the previous session. Anyway, we have to recall, therefore, the statement is given here. That is, if x is a random variable with mean mu and standard deviation sigma, then for any positive number c, we have probability of modulus of x minus e of x is less than c is greater than or equal to 1 minus variance of x by c square. In previous session, a Chebyshev inequality was given as p of modulus of x minus mu is less than k sigma is greater than or equal to 1 minus 1 by k square. This is what we have dealt in the previous Chebyshev inequalities session. But how this was reduced to this particular thing, that is p of x minus e of x less than c. Mu stands for mean. Mean means e of x, that goes like that. And you have to take k sigma is equal to c. Then what happens? If you take k sigma is equal to c, you get this inequality which is given in this session, that is less than c is greater than or equal to 1 minus, I have put k sigma is equal to c. So, k sigma is substituted as c. So, what happens to k? K is nothing but c by sigma. So, 1 minus 1 by c by sigma whole square. So, p of x minus e of x is less than c is greater than or equal to 1 minus, the sigma square goes up, sigma square by c square. But sigma square is nothing but variance. variance of x by c square. So, we have got this particular inequality from the Chebyshev inequality mentioned in the previous session. Okay. Now, what I am going to do is I am going to apply the Chebyshev inequality for the random variable x. For the random variable x, in the place of x, I am going to substitute as x1 plus x2 plus xn divided by n. So, we will apply this Chebyshev inequality for the random variable x1 plus x2 plus etc. plus xn divided by n. How this goes? Using Chebyshev inequalities to the random variable x1 plus x2 plus x3 etc. up to xn by n, we get for any epsilon greater than 0. I am going to write the Chebyshev inequality where in the place of x we will be substituting x1 plus x2 plus etc. xn divided by n minus e of x1 plus x2 plus etc. plus xn by n, which is less than c, is greater than or equal to 1 minus variance of x1 plus x2 plus etc. plus xn divided by n by c square. This is what is Chebyshev inequality applied for x1 plus x2 plus etc. plus xn, isn't it? The place of x I have substituted this particular random variable. Okay. Now, we have to simplify this. How the simplification goes? That is p of x1 plus x2 plus etc. xn by n minus that 1 by n I will take it outside, and each expectation is distributed for the random variable e of x1 plus e of x2 plus etc. e of x1, e of x2 plus etc. e of xn. This whole thing comes under the modulus, right, is less than c, is greater than or equal to 1 minus that 1 by n comes outside of the variance as 1 by n square, because a variance of a x is equal to a square variance of x. So, in the place of a you are having 1 by n. So, that 1 by n square comes outside, and this is variance of x1 plus x2 plus etc. plus xn divided by c square. What happens then? P of modulus of x1 plus x2 plus etc. plus xn divided by n minus 1 by n into mu 1 plus mu 2 plus etc. mu n is less than c, is greater than or equal to 1 minus variance of x1 plus x2 plus etc. plus xn is assumed to be bn, right, in the statement itself. Bn is equal to variance of x1 plus x2 plus etc. up to xn. So, we will substitute for this variance of x1 plus x2 as bn. So, then what you will have the remaining as 1 by bn by n square c square. Okay. Hence, if we assume bn by n square is less than epsilon, that is bn by n square tends to 0 as n tends to infinity, that is if we assume that bn by n square tends to 0 as n tends to infinity, what you will have? You will have limit n tends to infinity p of modulus of x1 plus x2 plus etc. xn by n minus 1 by n mu 1 plus mu 2 plus etc. mu n less than c is equal to 1. So far nothing is assumed about the behavior of bn for indefinitely large. Thus, having chosen two arbitrarily small numbers epsilon and eta, a number n naught can be found so that the inequality bn by n square epsilon square is less than eta will hold for all n greater than n naught. Now, consequently, we will have p of if we assume bn by n square c square is less than eta, then we will have p of x1 plus x2 plus etc. xn by n minus 1 by n mu 1 plus mu 2 plus etc. mu n less than c is greater or equal to 1 minus eta, that because this quantity is assumed to be less than eta. Okay. Taking negative on both sides, minus Bn by n square c square will be greater than minus eta, and that is substituted here. Okay. Is this the conclusion we wanted to see? Just see what is weak law of large numbers is. Arrived at the conclusion? Yes, I think so. P of modulus of x1 plus x2 plus etc. up to xn by n minus mu1 plus mu2 etc. up to mu1 by n less than or equal to epsilon is greater than or equal to 1 minus eta. Provided this condition in between we have assumed, that is Bn by n square tends to 0 as n tends to infinity. Hence, weak law of large numbers is proved for a sequence of random variables. These random variables are arbitrary. Next, we will state the weak law of large numbers for IIDs. Before that, the weak law of large numbers in a nutshell, what does it states? That is, with the probability approaching unity or certainty as near as we please, we may expect that the arithmetic mean of values, that is mu1 plus mu2 etc. up to mu n, actually assumed by n random variables will differ from the arithmetic mean of their expectations by less than any given number, that given number is c, however small, provided the number of variables can be taken sufficiently large, that is n is a number of random variables. We have taken sequence of random variables x1, x2 etc. up to xn, that n is nothing but a number of random variables can be taken sufficiently large, and provided the condition Bn by n square tends to 0 as n tends to infinity is fulfilled. So, that is what I told. If we want to test whether a sequence of random variable is obeying WLLN, you should test whether Bn by n square tends to 0 as n tends to infinity. What does Bn stands for? Bn stands for variance of x1 plus x2 plus etc. up to xn. This is what is weak law of large numbers in theoretic. Next, weak law of large numbers for IID random variables. This IID stands for identically and independently distributed random variables. Earlier in the previous sessions, we have dealt with discrete and continuous random variables. The random variables following various discrete and continuous distributions called binomial, Poisson and uniform, normal and exponential respectively. For those random variables, they are following different distribution. If all the random variables are following one distribution, that random variables are called identically distributed random variable. Identically distributed. One I stands for identically, and another I stands for independent random variables. Independent in the sense where the probability mass functions or the probability density functions of two random variables will be the product of their respective probability mass function and probability distribution functions. That is, identically stands for all the random variables x1, x2 etc. up to xn following same distribution, and independent in the sense p of x1 plus intersection x2. I am talking about events that can be converted for discrete and continuous with their respective probability mass function and probability density functions. That is, p of x1 intersection x2 intersection x3 etc. intersection xn is equal to p of x1 into p of x2 into etc. p of xn. That is what is independent condition. All these things are already discussed in the previous sessions. So, we shall discuss the WLLN for IID random variables. That is, if the random variables x1, x2, x3 etc. up to xn are independent and identically distributed, that is, if E of xi is equal to mu, that is, the mean of all the random variables are same, mu. If they are not identically distributed, we shall have E of xi is equal to mu I, that is, E of x1 will be having mean as mu 1, E of x2 will be having mean as mu 2 etc. like that. It is having a common mean, means all the random variables are identically distributed, and variance of xi is equal to sigma square. Here also the variance is also common for all the random variables. For all I is equal to 1, 2, 3 etc. up to n, then What does WLN for IID states? P of xi minus E of xi less than n epsilon is greater or equal to 1 minus eta is less than epsilon is greater or equal to 1 minus eta provided Bn by n square tends to 0 as n tends to infinity. This is weak law of large numbers for identically and independently distributed random variables. We shall do a problem in WLLN for IID random variables. Let xk be mutually IID. IID means identically and independently distributed random variables with mean, mu and finite variance. If Sn is equal to x1 plus x2 plus x3 plus etc. xn, prove that the law of large numbers does not hold for the sequence Sn. Now, in the place of x1, x2, x3 etc. up to xn, your random variables now are S1, S2 etc. up to Sn. So, we have to verify whether Bn is now variance of S1 plus S2 plus etc. Sn. We shall start the proof. We have to verify Bn by n square tends to 0 as n tends to infinity to verify, where Bn is variance of S1 plus S2 plus etc. plus Sn. But what is S1? S1 is just x1, isn't it? What is S2? S2 is the sum of partial sums up to 2 only. So, x1 plus x2. Similarly, what is S3? S3 is x1 plus x2 plus x3. Like that, if it goes, what is Sn? Sn is x1 plus x2 plus etc. plus xn. So, what about variance of S1 plus S2? I will write S3 also for clarification plus Sn is equal to, we have to convert it to xi's. A variance of x1 plus x2, is it, that is S2 plus x1 plus x2 plus x3 plus x1 plus x2 plus xn. Now, we have written S in terms of x's. Now, just count how many x1s are there. How many x1s are there? x1 is there here 2 times, 3 times, like that it goes up to n times. So, n times x1 is there. And how many times x2 is there? x2 is not there in the first term, but it is there in all the other terms. There are n terms, it is not there in the first term. So, it is there in the remaining n minus 1 term. So, n minus 1 into x2. Similarly, n minus 2 times x3 plus etc. What will be the last term? Xn minus 1 will be 2 times and that xn will be only 1 time. Last xn is only 1 time. Before that, xn minus 1 is 2 times. So, now just distribute the variance, because all xi's are IID. IID means independent. Independent means the covariance is 0. When you are distributing variance, the covariance will be 0. Okay, because of independence, the covariance is 0, and I will distribute the variance just like that. So, n square variance of x1 plus n minus 1 whole square variance of x2 plus n minus 2 whole square variance of x3 plus etc. Last term is variance of xn. Okay, and all these are sigma square, because variance of xi is equal to sigma square for all I. So, this is sigma square, n square plus n minus 1 into sigma square plus n minus 2 into whole square into sigma square plus etc. plus sigma square. So, sigma square is taken commonly outside, the remaining is n square plus n minus 1 square plus n minus 2 whole square plus etc. plus 1. writing in the reverse order, this is sigma square plus 1 square plus 2 square plus etc. plus n square. So, this is equal to sigma square into what is that 1 square plus 2 square plus etc. up to n square stands for? It is sum of the square terms, and according to the sum of the square terms formula, this is n into n plus 1 into 2n plus 1 by 6. Okay. Now, this is Bn, right? Now, Bn by n square will be sigma square into n plus 1 into 2n plus 1 by 6 divided by n square. 1 n gets cancelled and you will have n plus 1 into 2n plus 1 by 6n into sigma square. Now, as n tends to infinity, the numerator consists of n square term, denominator consists of n term. The numerator has got higher power of n. So, as n tends to infinity, the numerator being higher power, this also will be n by n square also will tend to infinity, which is highly a contradiction to obeying the WLLN. That is, as n tends to infinity, Bn by n square should also tend to 0. It should not tend to infinity. If it tends to infinity, it means that it is not obeying weak law of large numbers. Hence, we say that the law of large numbers does not hold for the sequence Sn, where Sn is the sum of the partial sums. Next, examine whether the WLLN holds for the sequence of IIDs defined as follows: P of xk is equal to plus or minus 2 power k is equal to 2 power minus 2k plus 1, and also P of xk is equal to 0 is equal to 1 minus 2 power minus 2k. We have to verify whether the WLLN holds. We shall verify this. Solution start like that. First of all, whatever be the random variables, we are supposed to calculate the corresponding variance. Variance is nothing but Bn. Bn is equal to variance of x1 plus x2 plus etc. plus xn. Okay. Finding variance of each xi, we have to find out expectation of xk first of all, and then expectation of xk square. Then only we can find out variance of xk. On all being identically distributed, we will take all xi's as xk, and then we will find out the variance of x1 plus x2 etc. xn, that is bk. So, what is expectation of xk? Expectation of xk according to the formula is summation xk into p of xk. Xk is having 3 values. What are the 3 values? One is 2 power k, another one is minus 2 power k, another one is 0. So, for first of all, I will take 2 power k. What is the probability? 2 power 2k plus 1 plus minus 2 power k into the corresponding probability is also minus 2k plus 1. What is the third one? 0 into 1 minus 2 power minus 2k. What does this stands for? 2 power k and minus 2 power k gets cancelled totally, and this is 0. So, we have expectation of xk equals to 0. Next is expectation of xk square we want. According to the formula, this is xk square into p of xk. Xk square is 2 power k whole square, corresponding probability is 2 power minus 2k plus 1 plus minus 2 power k whole square into 2 power minus 2k plus 1, okay, plus 0 square into 1 minus 2 power minus 2k. What is this equal to? 2 power 2k into 2 power minus 2k plus 1, and negative sign goes off, the plus 2 power 2k, 2 power minus 2k plus 1, third one is 0. Okay. So, this is equal to 2 power 2k and 2 power minus 2k gets cancelled, and similarly 2 power 2k and 2 power minus 2k gets cancelled, and you will have only equals to 2 power minus 1 plus 2 power minus 1, which is nothing but 1 by 2 plus 1 by 2 equal to 1. Okay. So what is this? It is nothing but expectation of xk square is equal to 1 we just got. What is variance of xk? Variance of xk according to the formula is E of xk square minus E of xk, which is equal to 1 minus 0 square is equal to 1. So we have found out variance of xk is equal to 1. So what is variance of x1 plus x2 plus etc plus xn? All are identical. So all can be equated to xk plus xk, because all are identical. Xk is equal to variance of n xk, n square into variance of xk is equal to n square into 1. So what is Bn? Bn is equal to variance of x1 plus x2 plus etc plus xn, which is equal to 1. Therefore Bn by n square is equal to 1 by n square, which tends to 0 as n tends to infinity. Okay. Hence we have proved Bn by n square tends to 0 as n tends to infinity, which means given random variable satisfies the weak law of large numbers. Based on the problem given, an exercise has been given to you, which can just go through, examine whether the WLN holds for the sequence of IIDs defined as follows. In this session, we have dealt with the weak law of large numbers. Also some exercises are worked out in WLLN for identically and independently distributed random variables. Thank you.